Okay, good morning, and good to see you all. Yeah, hope you've had a good week. So, if we were to look at the learning program for this semester, it actually says we're going to have somebody in from Revolution Roofing today, but I haven't organised that yet to get someone in. Apologies for not being hot on that, but we are still a fair way away from roofing as well. So maybe it's the appropriate course. But as we move through the tiles, so we've gone from empty site to thinking about what we're going to be building on that, to assessing a site, and then doing the preparation work. So today we're going to move on with concrete, and certainly I accept there may be some people in this class who are possibly even more qualified to talk about concrete than myself. So for those of you that have had a fair bit of experience in concreting, etc., and design of concrete, certainly appreciate your input in that regard. But the way that this is set out to look at concrete, we've got two sections, topic 4 and topic 5, as concrete the material, and then concrete structure and envelope. What I think is probably more appropriate to you, or probably the best way to start with this, is actually to have a look at concrete structure and envelope first, and then we'll go back to the looking at concrete as a material, because much of what's included in here, the concrete for structure and envelope, directly relates to how you guys think about the use of that concrete in the building. So, but just before we launch into that, any queries and so on in regards to assignments, etc., that I haven't clarified? I've had one or two questions via email in regards to that, but people progressing fairly well with that? Yes? No? Well, let me know if you're not. So it's 2 weeks to do it. It's, it is the sort of thing that if you can stay focused and you have a great deal of information at your fingertips, you can complete that sort of task very quickly. But I don't suggest you do leave it to the last minute. But certainly, if there are any queries, let me know. Morning. All right. So important to differentiate between concrete and cement. In fact, I guess before we get stuck right into it, might as well jump up and have a look at the various different things I've set out on the table here, because that, I guess, a large amount of what we're going to be talking about today. And yeah, come up from your seats and gather around the table so you can have a close look at it. Now, I guess a large amount of what we're going to be talking about today can actually be summarised in a few minutes of discussion. So, big difference between, so that's our bag of premix concrete. So just add water, you've got that. Give it a few hours. That differs from bag of cement. Bag of cement is one of the components that goes into here. If we want to make some of this, get some of our cement, some coarse aggregate, and some sand, mix that together, and allow it time to go off. That's the nuts and bolts, or that's the very simple story for concrete. But of course, there are many different mixing ratios for various different strengths and slumps and many different additives that we can also add into our mix to get different performance and different qualities out of that concrete. So with our concrete, certainly not all concrete is the same. We have concrete of different strengths. So 20 MPa for your standard slabs, 32 MPa for higher concentration of loads and polishing, etc. Also, typically in construction, we don't use concrete alone. Concrete marries incredibly well with steel. The thing about concrete is it's really good in compression. We can put a lot of load on top of that concrete, and it's not going to do anything. If I put a lot of load on this steel strand, it will bend. Steel isn't so good in compression, but steel is fantastic in tension. So we can use a steel strand like this for picking up, a great deal of weight, and that's why combining concrete and steel together, we get the best out of both of those materials. Just a really quick sort of nuts and bolts way of looking at things, and I encourage you to do this, to look at buildings, look at building components in this way as you go around, is that things are in compression and tension. And you'll hear me say that again and again and again and again through this subject. But let's say I look at this light, this light track up here. That's suspended from these cables there like that. It's hanging down. In between the suspension of those two cables at the base of that light support, that base is going to be in tension. The top of it is going to be in compression. As it wants to deflect like this, the material at the top gets squashed together, the material at the top gets pulled apart. That's going to be the same in any of the elements you see around the building here to a degree. So the mullions for our window there, now there shouldn't be any load placed upon those windows, but if there was, then those mullions are going to be in compression. But they're not just simply in compression, they're going to want to deflect one way or the other. If they deflect in one fashion, then the short side of that is going to be in compression, the stretch side is going to be in tension. That's probably something you know a great deal about. And so that's going to be the way with our concrete slabs as well. So we'll form up beams, and then the way that we design our raft slabs typically, now this is, I'm talking typical examples here, is to move around with the soil and carry the weight of the building as it moves around. So we want that raft slab to be able to do this. There is always some difference of load throughout that slab, earth, pushing up underneath it or subsiding. That will cause some elements of that slab to be in compression, some elements of that slab to be in tension. Our steel is to resist those tensile forces. So when we've got concrete beams that are wanting to do this, the steel down the base of that will resist that force. The concrete at the top of that beam wanting to deflect, the compressive strength of that concrete is going to resist that as well. So this is a piece of Hebel, this is a piece of aerated concrete, it's incredibly light, I'll pass that around. Notice that's got steel incorporated in it for tensile strength. And you see the big chunk taken out of that. We get a big chunk taken out of that because it's, that aerated concrete or concrete in general is not very good in tensile strength. That's why we can break sections off of it.
I've seen that.
Yeah. Pass that around. So I assume that's just a piece out of a veranda slab. So yeah, so that doesn't have air in it, that one.
Oh, definitely not.
Yeah. See, that one has some steel bars in it as well. However, those steel bars are not the same as these steel bars. That is the remains of this stuff, which is slab mesh. This certainly provides strength in our concrete, but its main intended purpose is to control shrinkage of the concrete, so that we get cracking happening where we want cracking to happen. This piece, that's a reinforcing cage, and that's a miniature one, sort of mocked up to show what we typically deal with. The size we normally deal with at maybe 600 deep, 300 wide. Take off 40 mil for coverage. But we've got some deformed bars, so those deformed bars bond well with the concrete, and then we have, holding those bars together, ligatures. Those ligatures space those bars in the correct spacing, and then we've got got tie wire tying the ligatures to the bars to make a reinforcing cage to ensure those bars are in the right place. This little thing here, that's different. That's not the type of thing you typically see in a residential slab. That goes, so yeah, I'll go into that quickly. That's, I guess, that's fairly simple technology in that, okay, it uses the compressive strength of concrete and the tensile strength of the steel to resist forces. But if we stretch steel before it gets bonded to the concrete, when we release the strain on that steel, it transfers that load into the concrete, slightly compressing the concrete and keeping our steel in tension. The reason we would want to do something like that is because that that diminishes the rate or the extent at which that steel will stretch before it holds. Because if we get some steel, we can stretch it a little bit and then it becomes harder and harder to stretch. So if we stretch it a little bit already and keep it slightly stretched, it's going to take those tensile forces a lot more straight away. And then if we provide some compression to the concrete already, then we're not going to have to deal with any compression of that concrete when it's upon.
I remember the throwers we used on the rail for train. They scratch the.
Yes.
Yeah. Exactly. I was in the factory how they make the.
Right. Great. Yeah. Yeah.
And I remember they scratch the steel and they added the concrete and made the throwers put under the track.
Yeah. Great. And then when that concrete has all gone off, it's all bonded and it's got its compressive strength, then you release those jacks and transfer that into the concrete, and then you take the stop ends away, and then you've got this pre-stressed beam.
Yeah. So there is that term, the pre-stressed, where they do panels, panels precast and pre-stressed.
Yes, most definitely. Yeah. And so in fact, I've seen some beams going in down here with the work here, and I could look. I didn't speak to them, but I'd be pretty sure that that'd be pre-stressed beams, because by doing that we can be more efficient with our materials. We can add properties to those beams to make them perform better with a smaller cross section. Hence, using less materials, adding less weight on site. And if we're going to be precasting elements in a factory, it's a great time for doing that. You can do this stuff on site as well. You can put in conduits. Well, it's like, so I'm just using the term conduits, but these sleeves in while you're forming up for your slab. So you put those conduits in, you pour your concrete, but you have your steel strands running through, and then your concrete is cast, and then you pour a non-shrink grout, or you pump a non-shrink grout through those conduits to bind with your steel. Hence, your steel is bound to that non-shrink grout, which is bound to those steel conduits, is bound to your slab. Then you release the pressure on those. So that's post-tensioning. So you've got pre-tension, which will happen in the factory, post-tension, which you can do on site. A major difference between those two, though, is if I had a concrete corer and I was cutting a hole through a pre-stressed, look, I wouldn't want to be cutting a hole through any sort of beam without understanding how it's all going to work and what I'm going to be hitting, right? But let's say I did. If I chopped through one of those strands in a pre-stressed beam, it's not going to be as bad as if I did it in a post-tension one. Because if I do it in a post-tension one, it can release that strain all the way through, because the grout doesn't have the same bonding capacity as the concrete does. So the concrete binds to that steel strand all the way through, whereas the post-tension, And so if I cut through one of these in a post-tension thing, the whole thing can go. So important to understand those performance aspects of those things into the future as well. And I haven't been following this thing. Was it in where was it? Is it in Madrid where the bridge has failed?
No, Italy.
Oh, Milan.
Yeah.
Another M place.
Yeah. down on the coast going towards fronts.
Mm.
So,
Yeah, but they may, but certainly there are, there are differences in the performance of those things. Now that goes a little bit beyond residential construction, but certainly interesting stuff to know. And yeah, possibly I don't know if you use any of that sort of technology or so in your.
Go tomorrow to my concrete that's doing the SA tilter. They're doing those.
Yeah.
Yeah, because I need an engineer now.
Yeah, yeah, and and this sort of technology does creep into residential projects as well. Not not typically, but sometimes. But back to our sort of bit more basic residential stuff. So these these are our ingredients for making some reinforced concrete. We'll have some slab mesh. Actually, let's take that one out. It's not residential. Slab mesh on the top, and that in our beams down the bottom. All right, go make a slab. We want to put some of that underneath our slab. That's to stop moisture coming through. So it's called a vapor-proof membrane. That's to ensure that we don't get moisture, because moisture does transfer through concrete, and we don't want to get moisture coming up through the concrete, which carries salts in it, and those salts being deposited on the top of the slab. Probably has everybody seen salt dam before? So deposited salts, they'll come to the surface of something, and then the water will evaporate, leaving the salt behind. The salt will form crystals, and it wedges off little particles of stuff. We don't want that happening. We don't want deposited salts just coming through on our floors underneath our carpet, etc. We don't want moisture in buildings in general in terms of condensation and mold growth and things like that in your buildings.
Use a product called Sealicrete.
Yeah.
It stops salt ingress also into your slab.
Yeah, yeah, and that's an admix, is it? That's something that it's added in.
No, it's actually painted on afterwards. It's like a liquid that actually goes into the concrete form by 20 mil.
Yeah.
I've been researching that because of the slab main cups. We're sort of looking at the fact that we're going to have to seal because it's in the air, and we've got salt.
Yeah.
Spray.
Yes.
So
yeah.
obviously for structural integrity, salt will get into your slab. So
yeah, yeah, and so you use that on the outside.
That's going to be used on the laid out slabs on the outside.
Yeah, cool.
On the top and inside.
Yeah. Sorry, what was the product called?
Sealicrete.
Sealicrete. Yeah, and that's so in that application, it's a it doesn't end up being it's like a bit of membrane that impregnates the concrete. It's not just one that sits on the top, but actually becomes part of it. And in that, you've got both positive side and negative side membranes as well. If we've got moisture travelling from here through to there, I put a membrane on this side, that's a positive side membrane. If I put a membrane on this side, that's a negative side membrane. So negative side membrane has moisture coming in behind it. Negative side membranes, and in the main, not as effective as positive side membranes, because moisture typically tends to affect the bonding as such. Although when you've got something which is impregnated, obviously it's got a far better bond to it. But essentially, what you're doing there is a positive side membrane, because it's coming in from the outside. Right. Also, with our concrete, we'll want to use some of these things as well to ensure that our steel sits in the right place. So they're bar chairs, and they've been formulated to make sure that those bars have the right clearance from the base, because we can't have steel right at the bottom of our slab, because as I said, moisture comes into concrete. If we have our bars sitting right at the base, they're going to be subject to more moisture. There's a chance that they'll be subject to more moisture. One of the things that happens with steel in a slab is that, well, in steel in general anyhow, whenever it rusts, it expands. So we get oxygen joining onto those steel molecules. They create a lattice work on a larger molecule that needs more space, and it expands. When you get steel expanding inside concrete, it cracks concrete. When you get cracks in concrete, you get more moisture, you get more rust, you get more expansion, etc., etc. So what we don't want to happen is any of that rust and expansion in the first place. And that's called concrete cancer, and you see it happen around the place with some older buildings.
Yeah, down at Seacliff, not far from the Seacliff Hotel, they just fixed it up for the balconies with the cantilever.
Yeah.
Concrete. It was just ready to fall down. You see all the reinforcing rusting away.
Yeah.
It was incredible.
Yeah, and then it diminishes the thickness of your concrete because it's busting all this concrete off the bottom. But then you no longer have the bond between your concrete and your steel reinforcing. So those two aren't working in concert, aren't helping each other out. And then and then eventually you get your steel completely rusting away, not having any tensile strength whatsoever.
So how much damage can white ants actually do to concrete?
Not much, from what I know.
From what I heard, they eat it. They love it. They'd rather eat concrete than timber.
No, I haven't heard that.
And we had our laundry. They left all the timber alone, but the concrete floor was just absolutely floored.
Well, that's that's the first time I've heard.
That's interesting.
Incredible.
Yeah. I just found some woodcrete blocks. I thought this would be interesting because I was just looking at different things and they're really cheap. And the blokes said, "Oh, you don't have to worry about termites." And then you sort of be going, hang on, a loose coarse concrete that they'd eat.
I've got no idea about that.
Yeah, I was surprised when they said that, and when they pulled up the concrete, but they were in there having a ball.
Don't know. Got no idea about that. So important to protect the steel, and obviously you've got other taller bar chairs that will put steel in places where we want it, because in talking about that compression and tension, it's important to put these elements where you want them, and we'll talk a little bit more about that. But then the other thing we do, if we mix all that together and just chuck it on the ground, even on some plastic, it's just going to go and fall out. What we need is stuff to keep it in place. So some formwork. That formwork has to be incredibly sturdy, and also what's important is that it has a really smooth finish. Important for a couple of reasons. One, because the finish of your formwork is the finish that you get on the edge of your concrete. On the not all faces of concrete are formed by formwork. You have your top face, which is troweled off, and we'll talk about that later. But any shape that's happening on your formwork translates into the concrete, and you can see that really well on that wall over there. You can see it from a distance in some regards, but then when you get up close, you'll see where they've used second-hand bits of form ply that used to have nails in it, some little pieces of the form ply that have come out, all that sort of stuff. Any defects on that face will show up in the concrete. So I'll pass that around, and you'll see some defects on that form ply, and that is going to provide a mark on that concrete once that concrete has gone off. And there are certainly ways to go around dealing with those defects and joins and so on. It's the silicon, so your silicon joins and you smooth them off so you get these perfectly flat edges, etc. for various different grades of concrete finish. But we'll need formwork. That formwork also has to be in place. It has to be put in place in a very secure fashion. What we do not want happening is whereby formwork falls over, and then we get concrete pouring out on site. Because, well, for one, just your standard 20 MPa concrete is going to cost you around $300 per cubic metre. You don't want to be buying more concrete than what you need. And so you order a bit extra for contingencies. But if you order, okay, yes, we've got this, and then 6-7% contingency, and then you get a blowout. Where are you going to get that extra concrete from to get your slab finished? And
Cost more than $300.
yeah, well that's it. You've got to get a mini mix out or whatever, and that's got to all happen in that time. And concrete goes off quite quickly. You'll see concrete is on site. They're flat out. It is really fast paced thing, and then it's going to be sitting around for a while, and then it's the final trailing off. But you don't want to have problems on site, and if your formwork's falling over, things are busting. There's plenty of problems involved. So basically, that's what goes into our slabs. This is aerated concrete. That's used for suspended floor slabs. It's used for wall cladding as a substrate for render. There are also Hebel blocks, although Hebel blocks typically don't get used so much now anymore. All right, we might as well head back to our seats if you wish, and certainly when you're passing some of these concrete walls in the TAFE, just have a bit of a look as well, and you'll see bits and pieces, and they'll give a bit of a story as to what was happening on the day when they were doing that. So concrete, something that's been used in construction for a very long time. So the Romans are famous for it, and I guess they're famous for it because it lasts a very long time. And for anybody who's spent any significant amount of time in Europe, there are places in Europe you can't sink a shovel without hitting some Roman ruins that include concrete. So it's something that dates back a long way, but as with just about any sort of building technology, there is always still innovation happening with concrete and different ways of using it and making it perform in various different ways. So things like adding, instead of steel, adding things like fiberglass, or there's even stuff you might have seen it now called polycrete, which is actually really something that's very different to concrete, but it uses much the same sort of very, very similar in its concept. So has anybody seen any polycrete stuff before? No one? No? If you go looking at service pits and things like that, or your Telstra pits and whatnot that are going down, a lot of those are made out of polycrete. So it's I think it's polypropylene, some sort of polymaterial that has sand and has aggregate in it. So it's behaving like concrete, except it's lighter. So this is, and as Doug mentioned, he's going to be having discussions with an engineer in regards to the concrete that's happening at your project.
Yesterday I wanted to pull out a bit because he's worried about the concrete joins and everything else. Saying I took an engineer to court and she's walked away from everything. So I've got no engineer now to sign off on her designs.
Right. Yeah.
I'm sort of like, okay, because there's so much going on that particular part. I spoke to the steel bloke yesterday because the steel's sitting in a yard up the hill ready to go.
Yeah.
The concrete panels go on top. I'm going to go and speak to Paul tomorrow because the builder now seems concrete laydowns have to have steel formwork that is exposed so it can all be, when a floater slab goes on top, stitched together or pulled back. He's just, as you can imagine, nothing's done. So he's panicking. So I put him back in bed and sort of said, look, I can get an engineer. I can get what it costs. But yeah, it's sort of like, even I'm worried about it because it's such a massive, 60 ton cement that we've got to tie back into the main structure.
Yeah.
And as you sort of look at that wall profile there, you might say, okay, well, the steel, let's pretend that cement there is the steel that's going to sit on top of the core. It's got steel bars that are going to go back into the garage.
Yeah.
With 32 mil bars. So it'll be heavy bars.
Very, yeah. Yep. Yeah. But Yeah, essentially, I can picture what you're talking about, because yes, there are certainly there are many, you know, pushing the envelope ideas, but the sort of stuff you're talking about, it, you know, it may not be done very often in residential construction, where you get the sharing of steel from one element to another. It does happen. Yeah, certainly in, you know, in aspects like this, where we've got some core-filled concrete blocks, and that's you know, it's got a reinforcing bar that comes down here, and it's got a cog on the end. So when you've got a bend on a bar, it's called a cog. That's bound to that beam, which shares that structure with our core-filled concrete block, which shares our structure with the slab. So they're all tied together. Yeah, you know, those things have certainly been done and done in a residential setting. But when we're talking about concrete and footings, etc., it's all very high stakes stuff. If something goes wrong with that, that's major. If something, you know, if something goes wrong with a door or something like that, later on we can go take that door out and we put a new door in. It's not really high stakes stuff. If something fundamentally detrimental happens with our structure, our slab underneath, the elements that form the structure of the building, typically there's very little you can do in a retrofitting situation to rectify those types of things. So it is a very high stakes situation, and so at that point in time, an engineer is involved. Now, not all structural engineers want to touch footings and slabs, etc. So I worked for a structural engineering firm that wouldn't do it. Right? Did just about everything, but when it came to slabs, that gets farmed out because of the insurance cost for that. It's just the frequency at which we had to do and specify slabs was not at that, you know, common enough to warrant having that insurance. That gets sent out to engineers, structural engineers that do have the insurance for doing that. So it is relatively high stakes work. So involved in that is the compilation of the footing report, footing inspection of trenches and footing steel. So they're going to want to assess the ground. They're going to want to have a look at how those beams, those footings have been formed up, to see if the result is going to be the same as what's been designed. Also, then these are just some by notes. So you employ an engineer for, well, engineering software gets used for designing trusses, etc. And for retaining walls exceeding 1 metre in height as well. Once again, a little bit high stakes scenario when we've got soil being retained and we're exceeding that metre, you've got to draw a line in the sand somewhere. That also, you know, can be high stakes in certain situations, probably like with your build as well. Where
two lots of retaining walls. One at the front of the house, where we're retaining the hill from the roadside.
Yeah.
And that's about 12 metres by 3 metres. The actual house itself, the front part of the former cat bomb shelter, it actually joins that retaining wall. That wall actually is part of the house, and also it's a retaining wall. And then at the back of the house, there is one section. At the moment, it's just dirt, but it's going to be dug away later, and that's going to have another 12-metre retaining wall, 3 metres high. We'll put the second part of the project in.
Yeah.
But at this stage, we're just going to leave the natural earth there for the moment.
Yeah.
Because that will have the whole house and the wall and everything. So we're letting that settle.
Yeah. Yeah. And yeah, don't want to so much get you to talk about dollars and cents, but I imagine that's, you know, it's fair bit that goes into that. And one job I worked on was the repair and reinstatement of a retaining wall that failed in Springfield, so sort of Mitcham area there, I guess, where it's worth spending a lot of money on something like this. A very, very tall retaining wall. I think it cost about $150,000 to do the rectification work for this. Now that involved augering large piers, tying sections of the new retaining wall back into those piers. It was basically to save a house that was sitting up in this elevated position, elevated above another house. So very difficult site for working in, but huge amounts of money, that can go into these things. Hence, you don't want to go designing retaining walls that are above that metre unless you know how those retaining walls should be designed and how things work in regards to soil loads, angle of repose, and moisture behind them, etc. Engineer establishes the worst case situation, designs the building elements to resist that loading. Various different loads we have to think about for design. So dead loads, live loads, wind loads, and then, well, I think we've got earthquakes, snow loads, etc. Not a great deal of earthquakes that happen here in SA, one minor one every now and again. Not a great deal of snow load happening here. But dead loads, that's all the stuff that is built into the building that you can expect is going to be transferring a load onto that building. The live loads, that relates to the use and the occupancy of the building. So these computers, I'd say they're a live load. The people in this room are a live load. There's not a great deal of dead loads in this room to speak of, but things like hot water services and whatnot in a residential aspect.
So would tilt-up concrete just make the engineer's job and the building planner's job a lot easier, because unlike bricks, where the job can go wrong on the site, on how you tie it in and everything else, whereas a huge concrete slab just bolted together, less room for error.
Yes, certainly. Yeah. I guess there are less steps for error, but the stakes are raised in certain other areas. So, and this was quite a while ago. So I was at the Yanko precast, and this is getting on about 8 or 9 years ago. I was saying a typical precast slab that comes out of here was about $15,000 worth, right? You make a mistake in that, that's $15,000 worth of mistake. Now that might be, that's if it's a terminal mistake. So stakes are high in that regard. But also, I worked on a job that was in a very remote location, a place called Freegon, which is just right out, way up north, in the north of the state. That was for a supermarket that had damage to tilt-up slab construction. Now, to just replace one of those tilt-ups that needed replacing, there's a lot that goes into that. You still need to have a crane up there. So all that equipment that you would have had for that one day, tilting up these slabs, you've got to bring back up there just for that one slab as well. And so in some of the rectification type work, there, stakes can be a little bit higher as well. Whereas if it's brickwork, you get some damage to a section, it's not as involved. So, but certainly there are trade-offs, and that is the way that building is going in general, is to get stuff off-site where it's dirty, messy, in the weather, etc., and an uncontrolled environment in terms of people aren't observed as closely, and get that happening in factories where it's all controlled, where you can have efficient use of materials, etc., get elements built there, get them onto site. So, so certainly that what you're talking about there is the general progression of things. Yeah. Yep. But with those, so got our various different loads, dead loads and live loads. Wind loads, so wind pushes against the side of buildings, wants to topple it over. So here we've got a building here. Now, so that's got some strap bracing in there. That bracing happens on an angle because as the wind pushes on this building, it wants to elongate that side. It wants to turn this from a rectangle into a rhombus. So pulling on this bracing here, now that bracing's not tensioned up. Of course, it's just a plastic strap. That bracing takes that tensile force, that tension load, and stops that building getting stretched in that fashion. Also, as we can see in this diagram here, wind goes over top of a building and wants to lift it up. So we'll suck it up. You know, and that happens with roofs. I've seen roofs pulled off the buildings and deposited elsewhere. What we do to stop the roof being pulled off is we fix it down to the rest of the frame. So that fixing down can be done with nails, it can be done with bugle batten screws, it can be done with strap, basically, and those decisions about how we tie that roof down relate to how many kilonewtons of uplift is going to be happening on that roof. Those tie downs, the ability to tie a member to a member is carried all the way through the frame until it's tied down to our concrete slab. So concrete, typically in residential architecture, gives us this raft with which the building can sit on and things can move around, but it also ties the building down into the ground, stops it getting pulled up and pulled away. And so you often see, you know, concrete pad footings have to be a certain size, not because they need a certain footprint to, nor not only because they need a certain footprint to be transferring loads down, they need to be a certain size to provide restraint against uplift for being pulled out. So compressive force, tensile force, fairly cool with that. Shear force, that's where you've got two compressive forces acting very close together. So it's where you want to create one piece sliding over another. So you know, probably some of you might know the click goes a shears, you know, song, whatever. So a shearing sheet, it's about those scissors, those shears that have two blades that act right next to each other for cutting. That's how a shear force works. And typically when we've got forces acting upon a building, we see the evidence of that is some deflection in materials. Deflection causes issues in certain ways. One is that it's unsightly. Now I'm just you know, broad brushing here. Typically people like things to look in straight lines and to be fairly neat. We don't like to have ceilings that sag and, you know, and beams over openings, etc., deflecting. You know, we typically don't accept that as a particularly good thing. But also, whenever anything deflects, let's say it's over top of our glass there like that, if we had the structure over top of that glass deflecting, that transfers load to the glass, which breaks the glass, etc. We don't want that happening either. So we want to minimise that deflection and or accept that there is some deflection that's going to happen and understand that deflection and to the extent that it's going to happen and accommodate that in either the right amount of gap in something so we don't get glass breaking, or in enclosing, so elements that do take that deflection, having them enclosed so we don't see that deflection in a visual sense. We may have covered this last week, but I'll reiterate again. Difference between foundation and footings. So the foundation is what our footings go on top of. So typically you hear those things mixed up a little bit in conversation and discussion about things. People say, oh, the foundations of my house are cracking. Well, the foundation is what you build upon, so the rock or soil found in its natural state on a building site. And those foundations can then be improved by bringing compacted rubble, etc., compacting that, producing a better foundation. But then the footing, that's the lowest element of the structure. So you're, in that case, a raft slab. Different types of footings. So integrated, raft slab, pier, and beam. So this is a piece of cable, but we can imagine that as a beam. We can, and I guess this is not a particularly good pier and beam because well, there we go. That's just a single pier and beam. So you can have a series of piers with a beam on top of that, and that provides you a structure. Now that might be elevated from the ground. It might be in the ground. Sometimes we use pier and beam or pier and slab to get loads transferred down to a reliable base. Our soil level might be up here, but all of that soil is untrustworthy, is possibly compressible or reactive or something, or we've got, you know, old cars dumped in it or something. We want to bypass all of that and get into something a little bit more solid. So we can auger piers, fill those with concrete and reinforce it, and then have our slab or beams sitting on top of that that creates our structure. And that may also be, you may have some structural systems that are a combination of those things. So we can have piers in sections where we have some unreliable soil, but there where we, well, unreliable foundation, but there where we have reliable foundation, we don't have piers. So you can have a mix of those as well. There are also strip footings, strip and beam footings, so typical strip footings. That's used in a lot of older houses. If we look at a soil map of Adelaide in relation to what soils are reactive, well, there's some fantastic soil that follows along the torrents. That's all lovely deposited stuff, which is not super reactive. But then we've got some reasonably reactive stuff happening around the centre of the city and into those parklands, etc. But then you've got some absolutely shocking stuff, sort of Newton Ross Trevor area, down around Port Adelaide and in patches around. But for anybody who's lived in place, you know, into those inner suburban areas like Unley, Parkside, I can't remember the names of those inner suburbs right on the east side there, but typically those places. What's that?
Felixstowe is bad.
Felixstowe?
Yeah, pretty bad around Trinity Gardens.
Oh yes, yeah.
All around there.
Yeah.
It's very reactive.
Yeah, and that's sort of getting on towards that Newton Ross Trevor bit as well. But we've got those areas that are they're not as bad as they come. They're not super worse, but you get in those old cottages, you get a lot of movement, massive cracks and things happening there. And the big difference there is the type of footings which are being used in those older cottages, which are just strips. They might be some big slabs of bluestone or some concrete, etc. But they're footings which is just simply a strip rather than a raft slab. Whereas later on in construction, you know, the invention of the raft slab, etc., has enabled us to build in places like Newton and Ross Trevor without actually having significant issues. Now, certainly there are significant issues that happen in that area. But if we were to go building one of these, you know, a place on strip footings in a scenario like that, we get a lot of movement. So the design of our footings plays a large role in that as well. So just a quick thing on soils, because this is what's going to tell the engineer how they're going to be designing those. Well, it's going to play an important role in that, is to look at the soil, whether it's stable, so it exhibits little movement, whether it's reactive, so it reacts with moisture, swells as moisture content is increased, and shrinks as it dries out, so it reacts to that presence of moisture. We've got some soft soils, highly compressible, that are unable to support loads. So I mentioned last week, if we've got soils that have got a lot of humus in them, a lot of organic matter, they can be soft, compressible, and unreliable. But then we've also got, you know, soils like that down around Port Adelaide area, and then we've got some collapsing soils. Now Adelaide doesn't have a great deal of collapsing soils, but there are some collapsing soils around South Australia. So I had a job at Renmark that suffered from collapsing soil. That's where typically you've got wind-blown sands where all your little bits are not fitting together perfectly. All your little pieces of sand, they're not fitting together perfectly. And they'll sit there and they'll take load. But then you add moisture to that and lubricate them and let them move and slot into their positions better, then that soil...
Use New Zealand playing in Christchurch when they had the earthquake and that sand became liquefaction.
Yeah, right. Yeah. Is that what you're going to say, Ina, as well? Is that what you're going to talk about as well?
Because I lived in Christchurch.
Right.
2008.
Yeah.
After when I'm leaving, when I was living, and then after 2 years,
2010.
10,
10, yeah.
you
10,
it happens.
Yeah, right. So it's not just moisture, but that vibration that enables things to settle, and then that structure is removed. So not a huge problem in South Australia, but it does happen. The best.
But if you got, like you say, if you've got these raft foundations that can cope with all that, like the waffle pods and it, but you know, it might sort of save the house, a wall from cracking, but wouldn't the whole building move?
Yeah, and it is so case specific. A large part of my old job was going around doing laser levels around a building to work out what's happening. You know, to look at it doing this. I think one of the biggest differences, actually no, the biggest difference I ever saw, one corner of the building to the other corner was 200 millimeters. So that's this much. That's the biggest. But I went around a building that had 150 millimeters of movement and had basically no cracking in it. And yet I've been to other buildings that only exhibit around 30 to 40 millimeters of difference and have significant amounts of cracking. And yes, that can be the result of the slab design, where if the slab is strong enough to carry all those elements and just do this very easily, well then, yeah, you've got your whole house doing that, and it'll crack pipes, it'll do whatever. But you've also got scenarios whereby you've got some soil which is pushing right up in one place, but then right next to it, you don't have that same force, where you've got differential forces happening within a very concentrated point, so it's getting closer to a shear force. And there you can have small amounts of movement, but that transfers straight into cracking of the building. But certainly, yeah, what we want, certainly we don't want buildings sitting on a tilt and whatnot. That's not it's not perfect case scenario by any means. And then we go damaging pipes and cracking pipes and exacerbating problems because we get more moisture under buildings and so on.
That actually happened in Victoria. I think there's a big court case going through where a lot of these houses were built on the waffle pod system, and the houses are all falling over or tilting over at different angles. But as building planners and designers, shouldn't those houses been put on piers rather than?
Yeah, possibly they should have. Yeah, and yeah, look, would certainly like to know all the things that go into those cases before maybe
you have it's not damaged, it's not cracking or anything.
Yeah,
it's just not sitting right.
And certainly the main motivation is to ensure that the buildings aren't cracking, that this isn't happening, and that idea of a raft slab is to enable that to happen, but still we don't really want that to happen to a large extent either. We don't want buildings going on a large tilt and so on. Hence, yeah, in some scenarios like that where we do expect that sort of thing is going to be happening, yes, you do piers down into solid solid foundations. And then you can talk about those sort of things for cars from home, but there are all sorts of approaches in that regard. And so the engineer's going to want to know about that soil that's underneath, there are different sort of soil reports that can be done. Some might be preliminary. You might get a soil report done early, before decisions around construction or purchase or anything. You might get soil reports done later when it comes to doing the construction. I think we've covered that previously. Yes, with the construction report, it details the type of footings that's going to be used in the building, any of the site works. So what's important to engineers also is not just the footing, but what's happening around that. What's happening with moisture? How are we getting rid of moisture? What we don't want is water pooling in places. You know, if we've got collapsible soil, we don't want water right next to the building, lubricating sands so that they sit close together. If we've got reactive soil, we don't want moisture sitting next to the building to, you know, make the clay swell in winter and then shrink in summer when all that moisture has evaporated. What we want to do is get moisture away from the building. We can do that with paving. We can do that with a ring of concrete paving around the building that slopes away to ensure that moisture goes away. We can think about what type of trees. So some of our eucalypts are fantastic water pumps. They are really good at getting moisture out of soil. They'll get the moisture out of the soil, it goes up through the leaves and goes out. That can be problematic for our buildings because in wintertime we can have plenty of moisture in that soil, but in summertime the trees are just pulling all that moisture out, exacerbating that movement. There are ways of managing that movement. So with adding moisture to soil, you know, through landscaping, through sprinklers, through moisture recharge wells, which are little things that sit in the ground and distribute moisture. I've drawn up several jobs for moisture recharge wells to ensure that buildings that their footings are not being stressed during summertime. So the construction report wants to also mention these type of things. What else should be happening on the site? It will certainly reference the bore logs, which are those soil samples that have been classified by the engineer. It will be done in conjunction with a contour plan. The slope of the land has an impact, and that's going to impact on things as well. Any cut and fill information, so that's going to have an impact on the design, and of course that paving advice, so what's happening around. So soil samples. So here's our hollow core. That's our sample of soil. Now this might be a very dry piece, and that might be fresh come out. That's the way it looks to me. But whenever you take a sample of soil down, well, essentially, you know, you're going through time. Well, in some instances, you're going through time, through various different layers of soil. So soil can be deposited in certain sections through various different events over time, and you get these different horizons of soil happening. The engineer will look at those various different horizons of soil and see see how to classify that soil, and those classifications. Although you'll get overall classification, so you get values for those various different strata, those various different horizons, but they're all summed up in creating a Y value. That Y value tells you the expected movement in millimetres of that soil through expected moisture exposure, sort of worst case scenario. And then that's going to be further classified into whether it's stable, moderately reactive, highly reactive, and extremely reactive. If you pour through a building contract, typically your standard form building contract will say, this is the cost of footings for a Class M soil. So if we're going to have moderately reactive soil, these are the footings, and so it's going to be $12,000 for your footings, Class M soil. But then you go to build, sign that contract, and then it's worked out you've got extremely reactive soils. Then the extra cost of those footings, because you're going to have far more significant footings in extremely reactive, that's put into your contract as a variation on contract. So when you see in a contract a mention of Class M soil, that's what that relates to. I can't remember the classification of Y values off the top of my head. I think they might be in the slides here for stable, moderate, highly, and extremely. Oh, and then you also, after that E, you've got P class soils as well. P class is something different. Once again, that's problematic class soils. That's for individual assessment.
So if I had H1D/P, that's a highly reactive.
That's so that's highly reactive, yeah. But that P that's in that D/P, that's not necessarily.
It says P problem.
Oh, it does. This says P problem. Okay.
So I'm just looking at the soil.
Yeah. Okay. So there's some problematic aspects to your soil. To go from H to P. Maybe I should. No, I think I know enough about this to be dangerous. Not enough to actually be specific about that. I talked before about our horizons of soil, our different layers of soil as we move through. These bore logs are split into looking at our soil in different horizons. And so what I can see from this soil report straight away is that we've got our different holes. So we've got 3 bore holes done. And I'll just quickly draw this up as I speak about it. So let's say we've got a site. That's our typical borehole marker, like that. So we've got 1, 2, 3 boreholes. It's important that when those samples are taken, that the location of our boreholes is accurately recorded, so we can then produce this plan. So typically our borehole location plan, so that bore log has to be read in conjunction with this plan as well. Yes, we can get some information from that separate, but the bore log and the plan assessed together gives us more information. So we've got BH1, BH2, BH3 like that, and then on top of that we'd probably have some contour lines showing us the slope of the land, etc. So I can see, okay, we've got 1, 2, 3 holes. Right down the bottom here, all of those holes go to 3 meters. What we might also see on some bore logs are where we've got 3 holes that go down, go to 3 meters like that, and then we'll have one that goes to 1500 mil. Can anybody tell me what that one at 1500 mil might relate to? Let's do it here.
Something like that.
What's that?
Pipework, something like that.
No, septic soakage. So if you've determined that your site doesn't have a sewer connection, and you've got to do on-site wastewater, if you're getting soil samples done, tell the soil sampler also to assess the area that you're thinking about doing your on-site wastewater as well, because you don't want to pay them $500 to go out there again to take just a 1500 mil thing to see how that for the wastewater engineer to work out how that wastewater is going to percolate into the soil. You want to get that done at the same time. This one, I'd say they've got a sewer connection there. They don't need a sample for on-site wastewater. But that tells me that then in borehole 1, we've got a little bit of horizon A, and then none of that horizon B1 and B and B1. It goes straight from horizon A to B2, then B3, and then B4. So if I was to do a visual interpretation of that, got something, let's say some land sloping like this. Like that, and then we've got B3, B4. So that first borehole taken through this. And then we've got our topsoil happening. So this is our humus layer up here. So that's horizon A. We've got that happening at the top there. So we've got a bit of that. We've got 400 mil of that. But then we don't have any B1 and B2. We've got B3 and B4, and then we're at 3 meters down here. Then we sink another one. Number 2, it's got 350 mil of topsoil, and then 350 to 1,000 is our B1. And then we don't, so that one doesn't have any B2 and any of B3. But then our other one has a different mix of, it's got lots of, it's got 300 mil depth of B. It's got 650 minus 650, that's 850, is that correct? 850 mil of B1. It doesn't have any B2 soil horizon, but then it's got a fair bit of B3 and a fair bit of horizon B4. Can everybody see that from that soil report? Think about those various different layers and what's being sampled there. And then for our various different horizons, the reason it's broken into those various different horizons is because the characteristics of each different horizon are different. So we've got A, silty clay, clay silt, dark grey, low plasticity. Then silty clay, dark grey, high plasticity. So this one's not very flexible, not very malleable. This one is flexible and malleable. This one, clay, black, very high plasticity. So extremely malleable. This soil is going to behave differently than that soil. It may have a different bearing capacity. If we put load on that, the bearing capacity of this may not be as great as the bearing capacity of that. I'm not going to, I'm not an engineer who can speak to that in detail, but the thing I can say is they're going to behave differently. Silty, gravelly clay, brown, mottled yellow, medium to high plasticity. Gravel is variably weathered siltstone. So these are our clays, etc., and then we're starting to get little bits of weathered rock in there. So rock fragments, bits of rock, and then once again, few pockets of variably weathered siltstone. So we're actually starting to get pockets of weathered rock, and clay with silt, brown, and dark grey brown, medium to high plasticity. So that's a lot of clay once again. So we've got a scenario happening where we've got a big chunk of clay, then clay with bits of rock and whatever, clay with a few less bits of rock, and then different levels of clay behaving differently on top of that. Each of those bits of soil and their depth and their reactivity is going to be assessed to get a Y value at the end. So our expected millimetres movement at the surface as that reacts to our worst case scenario of exposure to moisture. I spoke before slightly about differential movement being a problem just as much as total movement being a problem. If all of our Y values were 65, that may in fact be a better scenario than having 65, 56 and 54 together, because we've got, now that's not a huge difference, 56, 65, it's 9 millimetres difference in those Y values, it's not huge. But yes, our Y values are going to be a problem, but also the difference between them may highlight some problems as well. But that's not extreme. So various different types of slabs. So Eric mentioned before waffle pod slabs. That's what a waffle pod looks like from underneath. If you look at that from underneath, that's what it's gonna look at. Actually, oh no, we talked about waffle pod slabs last week, didn't we? Yeah. So slab on ground. So typically that's going to be a raft, slab, pier, and slab. So this is an underside of a bridge, but we've got a pier and beam, and then slab happening on top of that. Pier and beam. Waffle pod, grillage raft. Does anybody know what a grillage raft is? It's like your standard raft slab. So this is our standard raft slab here. That's got an edge beam there. A grillage raft just means we've got really deep edge beams. So that's the sort of thing you would see in these highly reactive areas like Newton and Ross Trevor, where soil's doing a lot of this, transferring a lot of load. It's about when we increase the depth of something, we increase its spanning capabilities. So this isn't about just using lots of concrete This is about increasing the depth of this member to enable it to span better. So it's being a little bit more efficient with those materials. We could just go, all right, let's do a massive piece of concrete here, but at $300 a cubic metre, that adds up. To design it so you just have deeper edge beams, if you don't have a great deal of shearing forces coming from the side, can work in scenarios. And then strip footings, as I mentioned before, your old cottages in Unley Parkside, etc., that have just, essentially a bit of a strip like this, and then the walls are built on those strips. None of it's all tied together. You get some different forces. Those elements have to operate on their own. They're not going to be as strong on their own as if they're tied to a slab on top. So that's the strip footings. So slab on ground referred to as raft slab. We'll go through this fairly quickly. So you clear the site, get all the humus off, and then you fill it and you compact that to get a good foundation. Now they're very nice looking trenches. Not every day you'll see trenches that look that nice. That's got what looks to be almost like sort of 90 mil to 100 mil layer of dolomite on the top. That dolomite, that's just crushed up rock, so crusher fines from the quarry. That gives you a very nice surface. Wet it down. It can be shaped nicely, and that's important because so this is some sort of fairly rough looking trenches. If our trenches are really rough, we need to order more concrete to ensure that we've got enough concrete to fill in all these little gaps, all the bits that we didn't calculate for. If we've got really nice looking trenches, we can order less concrete because we don't have all these little gaps that need to be filled, and we're not going to be using up our excess concrete beyond what was designed for. Also, so Eric was talking about slabs doing this before, and I mentioned, yes, that cracks pipes and whatever. That's what this spongy lagging is for. Well, it's the main reason. Take note of that. That is important because what we want to do is we want to create a space between our pipes and our slabs where we've got pipes that are going through a slab or through a beam like this. If that beam's going to be moving up and down, but the pipe is fixed, we want that bit of expansion, that bit of movement, that spongy rubber wrapped around there to enable that movement without cracking the pipes. Because if we crack pipes, that is a big problem. It's very difficult to go repairing pipes that are inside a slab. Yes, you can dig up pipes that are in the ground and repair them. Okay, it's annoying, but it's not the end of the world. Repairing stuff inside a slab is bad because you got to be
work inspected to that point.
Yes, that lagging should be in place. You can see all this lagging on these pipes before any of the steel has gone down and any of that plastic has gone down. Yeah, and
I didn't get the day when I did that. I didn't get down there to see what we actually did.
Yeah,
which drives me spare.
And it's not always going to be picked up. Now, council do have to be notified before a footing pour happens, so they can get in there and then check all that stuff. Whether that happens or not, that's not guaranteed. But yeah, it's important. And now I can't remember. So I had a slab engineer in a class last semester, and I can't remember what their rule of thumb is for their specification lagging, but it was like one layer of lagging for Y values up to a certain amount, and then 2 layers of lagging for Y values over a certain amount. So that's about if you've got big movement, more spongy rubber around the outside to enable that movement. You can repair pipes that are inside slabs. You sleeve them, etc. But it's just very annoying. And I worked for a plumber for a bit when I was still in high school. Had to cut through a slab and jackhammer up sections. It's not, from a structural perspective, that's not fantastic.
That happened to our place, brand new.
Yeah.
Someone started the side of the stuck some old plastic sheeting down the pipe.
Right, to stop concrete getting in there, I guess. And then
I think it just ended up. So they had to jackhammer the whole laundry up.
Yeah.
Expensive mistake.
Yeah, and these simple things, when we're talking about concrete, these very simple things that are not done properly initially, earlier, or simple mistakes can just be, can have huge cost impacts. And and you mentioned, stuff down a pipe. This is a good thing. All these pipes are capped, and that's fantastic. The reason that's fantastic is because when they're pouring concrete on site, they're not going to pour concrete down there. We want to make sure that doesn't happen. That's another thing. So all these, you do have to be thorough about these things. Moisture barrier. So that goes in. That's the what's that plastic moisture barrier I showed you just before. Lapped and taped at 200 millimeter. So 200 mil. Laps, so it's not just sheet to sheet. You lap it over 200 mil and tape it. There's some conjecture around that if you read through AS 2870 thoroughly. It doesn't say that you have to, but yeah, lap it and tape it is the general consensus on that. Reinforcing fixed into. So that goes into the trenches afterwards. So that's this thing essentially, drop down into the trenches to provide tensile strength where it's needed, right down at the bottom and at the top. We don't need a huge amount of tensile strength in the middle here typically. So we make sure our bars sit at the top and at the bottom of the beams. With corner details and whatever, you do have various different considerations. Wherever you've got re-entrant corners happening like that, you've got two levers that can work against each other or in concert with each other to crack a corner. And sometimes you have extra bars placed diagonally in those sections. As I mentioned before, concrete has to be covering all the bars, so minimum 25 millimeter top of slab. So inside the house, you need 25 millimeters. Outside the house and to the bottom, you need 40 millimeters to the cover of concrete to your steel. Another way of capping a pipe with some tape. As long as it works. This is another. I'll pass that around for you to have a look at. That is a very simple invention. That's just some stainless steel mesh. So it's a really fine stainless steel mesh that stops termites getting up into the building. So termites will typically not be able to breach a slab, go all the way through a slab. So we don't have to worry about where the slab is on the ground. If that slab's constructed correctly, we don't have to worry about it. But the areas we do have to worry about are right next to pipes, because as concrete goes off, it shrinks and will shrink away from pipes, giving us a few millimeters of gap there. That few millimeters of gap might be enough for termites to crawl in there and then enter into the house to eat wall frames, etc. So you just have that stainless steel mesh clamped around your pipes. It becomes part of that slab and stops the termites being able to get in. So here's some more reinforcing details. So that's some fairly significant reinforcing. Not as significant as 35 mil bars. That's
That was the top of that.
Yeah.
Where the columns go.
Yeah. So 35 mil bars. That's some massive bars. These ones, I don't know. Does anyone want to hazard a guess at what size those bars are from looking at that and scale? What do you reckon?
19.
19? Yeah. Yeah, I was thinking 16, but yeah, it's around the mark. So, and that's a fairly solid. So I see that and I go, okay, that's in a fairly reactive site. We've got 3 fairly large bars, 16, 19, or 20s, or whatever they are on the top here. We've got a lot of bars, once again, very large bars happening through there, and very deep edge beams. So that's a fairly reactive site there that's going into. We've got a very what appears to be quite a large rebate happening there, with our ligatures bent in a fashion to accommodate a fairly large rebate there. Although we don't have that rebate happening here. Not sure exactly what's going to be happening in that scenario. There may be a connection with a garage slab or something. Don't know.
Why isn't there any plastic to the right-hand side on that left-hand photograph? There's still mesh around it.
Yep, that might be a veranda. Yeah, it might be. Yeah.
So you save a little bit of plastic just because of that?
Mate, yeah. Look, yeah, and I'm of the opinion, yes, it's better to be a little bit careful about these things, a little bit conservative about these things. Surprisingly, that plastic's not cheap, really. It's not all that cheap. I can understand that builders go, oh, they'll save themselves $50 to here. There's a carton, or whatever they say, right? I don't. No, they never say anything like that, not at all. Yeah, look, I know they'll save themselves a little bit by doing that. Maybe because the law says they don't have to, and that once again, so go back to the NCC, the Australian standards, sets that base standard, not necessarily always the right approach. But yeah, good eyes for picking that up, spotting that. Also, at this stage, we can look at a slab. Typically, even if we don't know that building project at all, go, oh yeah, there's a bathroom happening there. They're having a separate vanity. This is that's our laundry, etc. So we look at the size of pipes and go, okay, 100 mil pipe here. That's got to be the toilet. Floor trap. That's going to be inspection for that plumbing run outside. So that's it, outside of the building. That 40 or 50 mil for our vanity. Yeah, not exactly sure which one of these is going to be which, but it might be laundry or so. So formwork has to be installed in a very reliable, rigid fashion. So staked and placed sufficient to resist concrete pressure from the pour, and also movement of people, etc., and what people are going to be doing on site as well. And it has to be placed accurately, because that's going to, where the formwork dictates is where the concrete's going to go. That concrete's a pretty permanent thing, so it has to be set out in a very accurate fashion. Also, yeah, it says oiled to allow separation as well. We want that formwork to come away from the concrete in a smooth fashion, not take little bits of concrete with it. So in placing the concrete, 1 day's notice of council and engineers for inspection. Yeah, concrete placement is a continuous process, or it should be a continuous process. Sometimes on major jobs, yes, you've got bits getting troweled off and so on, while you've got other bits getting poured in. I was at a job, a massive big shed. We were doing the tank next door to that, and they came over and said, oh, you don't have a bag of premix, do you? We're just like a barrow short of doing this slab. And it's like, no, we don't have any with us today for this. Yeah, how'd you go get? Yeah. But anyhow, they could do that because they've started that job hours ago, pouring that section right at the end, and they're working their way through. They're troweling off that section while they're still pouring this other bit. That happens in major jobs. Typically with your residential stuff, it all happens in one thing. It's not chaos, but it's a lot of activity right at the start there. When the concrete goes in, it has to be vibrated to ensure that all the aggregate, etc., settles properly Now that's not the result of poor vibration, but you get that same thing happening with poor vibration. That one, the reason we've got that sample is that doesn't have enough sand, cement, enough of your fine aggregates in there to get around your coarse aggregate. But when concrete is not vibrated down properly, you get air pockets in there. Those air pockets make that concrete much weaker because it's points at which there's little support, less compressive strength, and also maybe places for termites to live, etc. and whatnot. And so that concrete vibration has to happen. That's done by this shaft with a two-stroke motor that drives this little vibratory shaft, which is just jammed down into the concrete. It's important that shaft doesn't go whacking against your reinforcing. If it hits your reinforcing shakes around like this, pushes all the coarse aggregate away from that reinforcing. You get weaker concrete around your reinforcing. So a bit of an apprentice job, but also there's skill to that as well. So then the concrete goes down. The process of concrete placement, it's about starting off working with large undulations to smaller undulations to the point then that we might do a really smooth steel trowel finish like you see in a Bunnings warehouse or so. Have a look at a Bunnings floor next time you go to one. They're typically really good at it. Here, these ones are being polished a bit after laying. It's not a good example of a steel trowel finish. But first of all, you do your screed, which is a tough job. So you've got this screed and you're chopping and you're moving all the concrete across to make it nice and flat. And then you get the bull float on it, which is a really large trowel on a very long pole, and you're pushing backwards and forwards, just smoothing out all the bumps. And then later on, you do the troweling finish right at the end. So that's on a large job. That's like what I was talking about with that job where they need a bit extra concrete. They're still pouring this section over here, so that's all getting poured and done. But they're floating this one off already, and you've got various different trowels as well. So this type of trowel, that's a sit-on trowel where you've got two I don't know what they're called. Those two rotors with their steel trowels on that. That's the type of machine you get for a lovely glassy finish on the top. So you can sit on that, and it just whizzes its way around the concrete by tilting the blades. And you tilt the blades in one way, and it will provide pressure, and it just goes one way and the other, and vice versa. So you can sit on that and get a beautiful finish. You can do the same thing with this as well. It just takes you a lot longer. So, and that's the sort of thing, if you're doing concrete slab at home for your, I don't know, for your shed or driveway or something like that, and you want a good steel trowel finish to it, you go down to the hire shop and get one of those.
It's like that.
Yeah.
With this sort of setup, would this show up as cracking?
It may show up as cracking because that's the point of weakness, and you've got various different forces acting in various different locations. And yeah, if you've got a patch which hasn't been vibrated properly, it looks fine from the top, but it's all it's all loose down the bottom. That might be your place where it cracks, even though your forces are happening elsewhere.
Yeah, because from the top it looks okay.
Yeah.
Until something goes wrong.
Yep. Exactly. Yeah. Not all concrete is finished with a steel trowel as well, so that gets a very smooth finish. When we're going to be laying down carpet, we don't really want a really smooth finish on our slab because, well, especially with carpet tiles like this, if we're going to be sticking tiles down, we're going to be adhering anything to that concrete, then a really smooth finish doesn't work in our favour. So we might want a bit of roughness. Can anybody think of other scenarios whereby we want a bit of roughness on the top of the concrete?
Anti-slip.
Yeah, anti-slip. So footpaths. You'll probably see footpaths that are laid down, then they'll get a stiff bristle broom and do the broom over the top, and then just do the edges really nice. So they'll smooth off the edges, get those looking good, but then the whole centre section is all rough to give you to give you grip. Now that can be done footpaths and stairs, driveways, and so on. Yeah, and there's several ways of doing that as well. So with a stiff bristle broom, you get those lines. And I think if you look at the concrete as you head out from here, I think there are things like that happening in the concrete outside there. Oh, actually, that one out there, that's been the footpaths out there at the car park, they've been blasted away. So you get water to wash away all the fines from the top of your slab to expose that aggregate, give you more grip. So that's another way of doing it. But there's another way of doing it to get that sort of medium finish is to use a wooden trowel. So a wooden trowel gives a different finish to the steel trowel. Steel trowel is a very smooth finish. A wooden trowel sort of sucks the moisture a bit and makes these tiny little peaks. So as you go over with a wooden trowel, you get this rough surface happening on top of your concrete as well. Some more pictures of things. So yeah, some fairly standard slabs. This little bit here, that's what's called a set down. The reason you have a set down is because you don't want, because they've got a floor trap happening here. We want to ensure that any of the water that comes out of the hand basin or the shower and the door is left open, whatever causes moisture in that or lots of water in that bathroom is going to go down that floor trap. So you want to ensure that floor slopes towards that floor trap. You also want to do the whole thing slightly lower than the rest of the floors in your house. So in case there's some, like a toilet blocked or something and something, the system's broken, it's just like pouring water in there, but that water goes down that floor trap and not out into your lounge room or anywhere else into the building. So you create a set down in the bathroom, and that set down, so you've got slope relationships as set out by the National Construction Code as to what minimum slope you need on your bathroom floor there, and then you calculate your set down accordingly for that. They've also got a separate set down for the shower here as well. And in scenarios where you're doing an elevated floor, let's say we've got plywood flooring or something like that, we're on stumps and we've just got this flat floor, this platform floor, for that scenario you can't do a set down. So what you have to have in that scenario is overflow protection on all of your things. So it's a bath with a little hole right near the top that's attached to a pipe. So in case you leave the bath running and then you go out to a call or get on the internet or whatever and forget about it, that excess water is just going to go out through that overflow protection rather than onto your floor. Same thing with your laundry tub and hand basin, etc. Also, you can use a preformed shower base. So that one would probably not be a preformed shower base. That would be where we've got tiles going down on the floor, and you probably know a little bit about that. So you're part of being a tiler. But to save on doing that sort of stuff, you can just buy one of those shower bases from your hardware store and put it in there, and that stops that moisture or that water going out into here because they've got a lip on them. And so there are different considerations there and different considerations in regards to waterproofing as well. But because we've got a separate set down happening for that shower, that tells me that they're most likely going to tile that shower. So a carport happening here. The reason I suspect that's a carport and not a garage is because we don't have any rebate here for brickwork, but there's a rebate on that slab there. But once again, that slab is set down slightly lower than the rest of the house, because if we've got wind and rain coming in from this side here, we want that little bit of lip of slab to ensure that that wind and rain's not going, that water being driven across the flat surface of our car park, our carport isn't going into our wall frames. Just some interesting things to see in the background. There we've got some OSB sheet bracing there to help stabilise that frame. We've got some what do we call it, engineered floor trusses there, and we'll get onto all that sort of stuff later. some blue timber here, so that's been H2 treated for termites, so and some of them are treated for fungi as well. Strap bracing happening here, so type D strap bracing to resist that. Anything else people can see in that picture that's of interest? Anyone at this stage?
There's not too many noggins going across, are there?
No, there's not too many noggins. So the thing with noggins are that your noggin spacing has to be at 1350 centres. So that tells, I'd see that, and straight away I go, oh yes, 2700 high ceilings. Because we've only got one row of noggins in there. If we're going to 2900 high ceilings, then we need 2 rows of noggins in there. Yeah, and that yeah, look, I'd actually, yeah. Yeah, we're certainly less than 600 mil between our top plate there and our window head height. Typically your window, I was going to say typically your window head height's 2100, that window 2400 is pretty much the standard these days for that. But yeah, a clear indicator is, yeah, our rows of noggins there. But we'll talk more about noggins and studs and all those bits and pieces later. With concrete, yes, it's important to get it all right up until this point, but also curing is very important. If we just pour our concrete and then just let it dry, it's not going to be as strong as if we slow that process down. So if we cover it up with some material, like so we put some plastic over top of it, keep a fine mist of water over the top of it, or spray a curing compound on the top of it, slow that moisture loss down, we'll get a stronger bit of concrete as a result, because part of the strength in concrete happens because of those chemical bonds that are happening and allowing it time to form those strong lattices within the structure. So you slow the process down. That's what curing is.
Is that temperature related as well? Like, if you were pouring concrete, today on a 15-degree day versus a 40-degree day, using a curing compound to slow it down so it don't happen rather than temperature, outside temperature effect.
Yeah, so temperature has an effect. Yeah, certainly. You can't always pick your days, you can't always pick the weather. You try to, and the weather is going to have an impact. So there's various different weather considerations. One of them is that heat in curing, and there's certain things you can add to concrete as well although typically it's done to make the job easier or possible for the people placing the concrete, is like additives to slow the reaction. So that's about making sure that they can actually get that concrete in there and get it all placed and finished and so on correctly within the time they're given. And in winter time, so your concrete suppliers will ask you whether you, I forget what the term is now, but they'll ask you whether you want concrete which goes off quickly. Because if you're getting concrete delivered at, well, typically you'll see concreters on site at 7 o'clock in the morning. They want to get that in as early as they can, because they're going to be having that mad dash of placing it all, getting it all ready, and then they'll be sitting around for a while before they can finish it off. They want to be home, to watch the news at 5 or whatever. So they're out there super early in the morning. But if you're doing this in winter time when there's less heat around, it takes longer for that concrete to go off. And so concrete suppliers will offer you, accelerants in your concrete to make it go off quicker. So you can, so you place it and then you can be done, at a reasonable time in the day. But yeah, certainly you do want to. So the ideal sort of thing is to be placing concrete actually on a daylight today. It's really pretty good. Like daylight today is great. Not a lot of sun. It's not really hot. You're not going to have concrete going off really quickly, but no rain. You don't want rain on your concrete. You don't want water messing up that top surface, because it dilutes the cement on the top and makes the top weaker. But yeah,
Is SLUMP and MPA related together?
They are. So what a major driver of your concrete strength, so your MPa, your megapascals, is the cement to water ratio. Certainly the ratio of your large aggregates and the quality and the qualities of your large aggregates and your small aggregates play a part as well. But one of the major factors is your cement water ratio. If you have a lot of cement to a little amount of water, I'm just doing it in a nutshell. Don't apply this rule all the time, but in a nutshell, there's a simple explanation. A high cement to low water ratio will give you high strength concrete, but it will not give you much workability. So that concrete will not have much slump. You tip that bit of concrete out of your testing thing, it'll go like this. You know, it won't be slumping very much, but that'll be a high strength concrete. If you can work that into the scenario you need, well then you get a very strong piece of concrete. Sometimes we want a very, like a lot of slumping concrete. Sometimes we want that concrete to go like this, when we've got to get it to go into, you know, some tricky formwork and various like precast stairs or cast on site stairs, all this sort of thing, where you've got to get it to form into these scenarios. So yes, but there is definitely a relationship between slump and strength. So you're less, typically your less workable concrete is higher strength. Some details there. So just be aware this detail exists here in case you want to refer back to it. I think I've drawn this detail a few times already. We've got our top and bottom bars happening there. We've got our rebate for our brickwork. Our brickwork sits down lower than our timber, our structural timber. And for anybody who wants to describe brick veneer for their first assignment, for example, maybe that's a good thing to look at. It shows you your structural timber frame and then your veneer of brickwork and how that sits on your concrete raft slab, and how all of that sits above the ground. I haven't looked at this just recently. I do remember there was something funky happening with these measurements. Don't take those measurements for granted. Can't remember what. So yeah, 340 millimeters. That's an odd one because your excavator buckets come in 300 millimeter increments. But yeah, some funky stuff happening with the measurements. Be aware of that. But conceptually, that's what's happening, and this is all good. So 110 mil width of brick, 50 mil gap, yeah, 40, 50 mil, it's pretty typical, and then 90 millimeter stud work. So 250 or 240 mil is a pretty typical wall thickness there for brick veneer. Yeah, some more less common details, probably less pertinent to what we've got to talk about. Oh, that's a detail you might use a bit. You might use that at your place. I don't know where you've got. Nah.
Next slide, you will see mine.
All right. Okay. We'll go on to the next slide. Oh, that one.
The slide that shows.
Right. Okay.
That's like mine.
Yeah.
Except the square bit I've got along the back edge of the house. 8 round piers that go down 5 metres by, on the back of that, 5 by 600.
600 mil.
So they'll piers like that going down, and then it's got the rafts.
Yeah, it's sitting anchored on top of that, so it's transferring all that load down into a more stable substrate there, and letting the earth do whatever it wants in that space in between. Cool. So yeah, we'll get onto that fairly soon. But yeah, this detail here once again. So actually, oh no, I was going to say that's for Caulfield. No, what we've got happening there. Yeah, I won't go into all that stuff that's happening there. We'll cover all that later on in masonry. Yeah, won't digress with that too much. So various different systems here, waffle pod, pier and beam, pier and slab, and our grillage raft. So we spoke about those. So waffle pods, we've spoken about those a little bit. So that's about our big styrofoam boxes that go there to create a void. So that's about eliminating concrete, and they're all spaced with these things. So those things provide those spaces. What are you laughing at?
Oh, there's a story to that one.
Yeah.
The guy that came up with it forgot to patent it.
Oh, right.
And someone worked it out.
Yeah. Well,
so they paid royalties to the wrong person.
Yeah. Well, it's not rocket science. But, so they create that space between your waffle pods and vicariously create the beams that sit to make your slab something like this. And then we've got some bar chairs happening there with our slab mesh sitting on top of that to control the cracking in the concrete. No, we'll flick through that very quickly. And so that's what you'd end up having, something similar to that underneath. So that's a void former. That's not necessarily a waffle pod, but and this is another form of void former. I can't remember the name of that. But once again, instead of beams, you've got lots of little points of contact created in that one. So that one you're going to end up having a slab which sits up, and instead of beams, you've got all these little piers happening underneath it. So all these plastic bits are to stop concrete going in there. So it's about using the concrete more efficiently.
The most recent one I was saying was on the South Road project, with bridges with the beams. They using these black plastic balls.
Right. Wow.
And it's really nicely done because the reinforcing mesh is the actual spacer for the ball. So every second hole gets a ball put in.
Yeah.
It was beautifully simple.
Yeah. I've only seen that in pictures. I haven't seen that in applications.
Well, I saw it on a truck, and there's a yard down on the South Road where they set it all up. Incredible.
Yeah, cool.
Just so simple, you wonder why no one thought of it.
Yeah. Well, somebody has thought about it, and they're doing it. Yeah, and that's it's about going. Look, we don't need concrete in this spot. We don't need any compressive strength happening here, right in the middle of that thing. So let's not put concrete in there because concrete's expensive and it's heavy. Let's put our concrete exactly where it's needed. So that's what these various different void former technologies are all about. So onto Doug's place, where we've got piers that are going down into soil. Now that, as I mentioned before, that might be because you need to go down in the soil to find a very solid substrate for transferring lots of load to. It may be because you have soil here which will collapse under the designed loads, or it may be that you've got soil which is quite reactive. You actually want to be picking your elements up off that ground, but then still having your piers go down into something solid to allow that top bit of ground to move. So there are various different reasons why you would have a pier and slab. And there's several different ways of constructing piers as well. They might be piles rammed into the ground, and in places like Amsterdam, construction sites in that initial process are very noisy because you've got these pile drivers doing whack, 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 driving these piles down into the ground, for which they then build on top of because they've got some very sloppy sort of soil there. But there are also screw piles, if I mentioned screw piles before. So you can screw them down into the ground and use those in conjunction with slabs or elevated slabs, etc. Or you can auger out earth, fill that with concrete to create piers. And there's even a thing called bell piles. So I mentioned bell piles before. That's where you've got an auger that digs a hole and has a bit that flicks out. So you've got your auger doing that like that, and then does this thing at the bottom there like that. So you dig a hole, and then it's able to scrape this earth out and get that out. So you've got a pier that has a bigger footing, so like better sort of bearing onto the soil, but then also locks that pier into that soil as well. So go through that quite quickly. I'll skip over that. Pier and beam. So that concept with that is where we have piers, but then we have, rather than a slab, we have beams. So much like a lot of your bridge construction, or in where you've got elevated timber floors, you'll also have a pier and beam type structure, because you've got your bearers there happening on top of your piers.
Would you know what type of soil is actually on this side? Because what I found, where there's big factories or big government buildings, that's usually very reactive soil, because only the government can afford to build on it.
Interesting theory. I haven't heard put before. Well, we've got 10 minutes. Let's have a look at a soil map of Adelaide, if we can bring one up. So well, we'll just quickly go through the rest of these. So grillage raft, I took you through earlier. Some important things to mention about those grillage rafts. So sometimes you've got beams that are about 1,200 deep. Now, I'm not sure, I don't actually know why, but quite often those grillage raft slabs will be poured in a two-pour process, so they'll get the beams happening and then they'll do the slab after. Exactly why, I don't know. And then strip footings. That's where you've just got a strip, in this instance of concrete, and then your structure relies upon those strips. Those strips are not tied together with a slab, so they're not working in concert, and hence this type of construction is often far weaker and won't handle reactive soils very well. And then you've got some, so for your wind turbines and things like that, you've got some crazy footings happening for those. Here's an interesting scenario with very deep formwork happening, forming up basically a retaining wall with some steel reinforcing in there that might be carried through into other structural elements. No, that fast tube, I haven't looked at what that is. That's something that Jason's put into the slides here. But you also have, I can't think of what they're called now. I can't think of the product, but tubes that when you auger piers, that you slip these tubes in there and you pour the concrete to give the sides of those piers a very smooth side, so that your earth, as it expands and swells with moisture, it can go up past your piers, move past your piers really well as well. So there are these little sleeves that you can buy for doing that as well, but I can't remember the brand or the name of those ones. But that basically there's that concept of having smooth sides to your piers to allow the soil to move past and not impact upon your piers. Some interesting results from concrete. So just quickly, I'll just go back to here with our final 6 minutes. See if we can get a decent. Oh yeah. Well, actually, maybe that next one is the better one. If we can see it to decent detail. So I'm going to open up. Yeah, I don't know. It's pretty good. Yeah. So yeah, as I mentioned before, so that bit along the torrents there, that can be some very good soil to build on. But it's only in certain aspects. So one place I do know fairly well is Harrow Road in College Park. Down this end of Harrow Road, there at College Park, fantastic soil for building on. Drive down the road, and you into this heavy red brown clay, high chance of cracking. So you go from lovely stuff to some terrible stuff on the one street there. But yeah, so layered sediment of model marine and river origins, little likelihood of cracking. So that's in these bits here. But you do have other problems happening with sections of soil throughout that Port Adelaide region, though, as well in various little pockets. Yeah, so silts, sands, gravels, that's all this stuff here following on the torrents. You can see the torrents very well. You can see that floodplain type thing as it happens out there. Adelaide Airport's on the greener one. So that's all right. Sorry, this I think that. Oh no, that yellow one is these pockets here. We've got because the Adelaide Airport looks slightly different than our torrents in hue. I don't know why. Although, yeah, along these sort of tributaries as well, you've got same sort of thing happening there. But I mentioned before, yeah, Newton, but also Gillis Plains, etc. Black to dark grey clay soil is the worst soil in Adelaide. High likelihood of significant cracking. So you got some of those pockets. So fantastic stuff for growing things in, but not fantastic stuff for building stuff.
So Tonsley Park's in a pretty reactive.
Yeah. So where up? So is this Tonsley Park here? Was it? Is that large? Maybe we've got a large thing here without. I'm thinking maybe this thing here is Tonsley. I don't know my roads around here all that well, but yeah, we're in that sort of that heavy red brown clay, high chance of cracking. Although I've got to say that's much the same as the.
Already on the place.
One area between Macquarie Vale and Malunga, that sort of belt that runs across towards Orpinga. Forget brown clay. It's black.
Yeah.
It's black. It's just like you go there in summer and watch it open up.
Yes.
A good inch.
Yeah.
And it's all for the vineyards, but so it doesn't really matter. But you never want to build a house on that.
Yeah.
And it's steep too.
Right. Yeah, and that's the major contributor.
So
If you've got
dig it out like as if it's a humus, and it does look like a humus layer.
Yeah.
But it's I've been in a paddock sort of Western Falls riding for it. It's
down to the axles.
Down to that sort of level. Good movement of the heart.
Yeah. Yeah, so fantastic stuff growing in, and so Macquarie Vale through Wollonga, whatever, plenty of growing stuff happening, vineyards, and what not. And look, I has a guess at saying it's probably going to be similar sort of stuff to this here. Yeah. So that soil map exists, a nice sort of summary of that. So have a quick look, think about where you live and whatnot, and where if you live somewhere on that map, and how that impacts on you. Yeah. Well. Yeah. Yeah. Right. All right. Well, I'll stop the recording at that. There we go.